All right, section 4.2 for discrete mathematics gets into different base representations, and it kind of digs into the nature of our positional numbering system. We have a numbering system where the position of the digit tells us like how big we should consider that. Like we have a ones place and a tens place and a hundreds place and so on. That's because we use a base 10 number system. So first of all, let's go over that. Base 10, positional number system. So if you take a number, like let's say 2,397, okay, we interpret that number with this positional system as this is the ones place, so it's 7 times 1, and then add to that this 9 in the tens place means 9 times 10, so that's 90. 3 over here in the hundreds place means 300, and 2 in the thousands place means 2,000. So we add those together. Okay, so this means that 2,397 can be written as 2, 3, 9, and 7, each multiplied by a power of 10. So the 2 is multiplied by 10 cubed, which is 1,000. And then we add to that 3 multiplied by 10 squared, which is 100, plus 9 multiplied by 10 to the power 1, which is just 10, and then plus 7 multiplied by 10 to the power 0, which is just 1. So we have 0, 1, 2, 3. Increasing powers of 10, each multiplied by a number, and then added together. That's how to interpret this. So now that's base 10. You can do the same exact idea in other bases, where you can change the value of this exponential base here, base 10, 10, 10. I can change this to be some other number. But whatever number we choose to change it to, the available digits that we should use in that system get smaller, get fewer, rather. So, and smaller as well. So like in base 10, we have the numbers 0, 1, 2, dot, 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 all the way up to 9, right? Those are the available digits in a base 10 number system. But if we were to do a different number system, say base B, okay, I'm just going to, first of all, just not specify what number we're going to use, but have B be the base. B should be a positive integer, okay? B should be a positive integer, and the available digits, 1, 2, dot, 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 all the way up to B minus 1. Okay, so the available digits are 0 through B minus 1. And then, if you want to represent a number, say a number n, in base B, this would be represented by a sequence. It's the string of digits selected from this set. And so that string of digits is going to be like AK minus 1, AK minus 2, dot, 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 down to A1, and then A0. Right? So it's a string of digits like that from this. And the K is just the length of that string, so it's kind of the order of magnitude. Now, when we represent that like that, this is a positional number system, just like how, 2,397, the position of the digits matters. So the order matters. But if you want to indicate that this should be interpreted in base B, you put parentheses around it and a little subscript B on the end. So 2,397, if we put parentheses around that, we can put a subscript 10 to indicate that this should be interpreted as base 10, which means that each digit is multiplied by a power of 10. If it's base B, then that means we should interpret this as AK times B to the power K, and then plus a K minus 1 times B to the power K minus 1, plus all the way down to plus A1B to the power 1, and then plus A0B to the power 0. And you may have noticed that this looks a heck of a lot like a polynomial. In fact, it is a polynomial in the variable b, essentially. And then if you give b a value, then that produces the number that string would represent in that base b number system. So a couple of common examples, common bases that are used, other than 10. One is probably the most common base used other than 10 is base 2, which is binary. Okay, but we also have base 8, which is called octal, and base 16, which is called hexadecimal. Base 2, base 8, and base 16 are 2, 8, and 16 are probably the most common bases used in programming or computer science in general. I do want to mention one other base, which used to be very common, and that's base 60, which is the called sexagesimal system. Sexagesimal. And base 60 is a historically important base because base 60 was the base for the number system of the Babylonians, who were the first civilization, as far as this is my recollection, from when I took history of math. Babylonians were the first civilization to have a positional written number system. And they used a base 60 system. And I want to take a minute to explain something cool about base 60. 60 is a multiple of 12. It's 5 times 12. And the Babylonians had this really cool way of counting on their hands, because you'll notice that on your fingers you have 3 segments per finger, and they're very easily distinguishable by the creases in your fingers. So 3 times 4, you have 12 segments on your fingers over here, and you can use your thumb to count which one you're talking about. And so you can use your thumb on your fingers like this, right? And count like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then every multiple of 12, you can put up a finger. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and so on. And then kind of go like this, and then kind of go like that, and that gets up to 60, right? So they had this way of counting to 60 on their fingers and keeping track by touching different segments. That makes it sound like it's a base 12 system. It wasn't exactly a base 12 system. The way they wrote their numbers, it did end up being base 60. It's generally considered base 60. It is a little weird the way they wrote them with like little tick marks, but they had different types of tick marks that represented groups of, I think they were groups of 12. So it kind of it's a base 60, but it has sort of like a base 12 element to it, kind of embedded in it. Anyway, it's cool. It's a cool one. So we're going to do some more with base systems and look at a few algorithms.